Yeah, I'm going to be talking about machine learning for a particular type of discrete optimization problem, namely price optimization. And this will be under buyer and seller uncertainty. And this is joint work with Wenshou Guo, Nika Hagtalab, and Kirti Kandasamy. So just to say a little bit more broadly about my research interests, so a lot of my research has been focused on using machine learning to improve discrete optimization, looking at problems like integer programming, clustering, dynamic programming. But in this talk, I'm going to talk about what I see as a specific kind of form of machine learning for discrete optimization, namely machine learning to improve mechanism design. And why is this a discrete optimization problem? Well, in mechanism design, you have a bunch of agents who are all interested in some set of items that you're selling, and you want to find a way to allocate those items among the agents in such a way to maximize revenue. In the end, this ends up just being a discrete optimization problem. So to put some context around the particular problem I'm going to be talking about, so online shopping now accounts for 22% of global retail sales. And one of the most valuable aspects of online shopping is that customers are able to make far more informed purchase decisions than they ever have before. And this is because they can gain insights from hundreds or thousands of reviews for items before they go ahead and make a purchase. To make sense of this trove of data, buyers often use reviews by others who share some type of theirs. So for example, this would be their body type when shopping for clothes, or skincare type when shopping for skincare products, and so on. And the buyers will then use these reviews to estimate how much they value the item for sale. And the value for these items for sale might be quantities that they're kind of uncertain of a priori. So to give a few examples, here's I recently got a cat, so I was looking at grooming brushes. And this seems to be pretty well reviewed, but if you go in and search for long-haired cats, you'll find that, okay, this brush is actually not particularly well suited for long-haired cats. Similarly, here we have a pair of pants, pretty well reviewed. But if you zoom in on people with a particular type, namely an athletic body type, then you'll see that, okay, people with athletic body type find that these pants are actually not particularly flattering. And finally, this skincare product, if we zoom in on agents who have oily skin, then we'll find that this is a really great product for oily skin. So the key challenge that we face when figuring out how to price the items for sale, when buyers are learning from reviews, is that for rare types of customers, for example, among athletic body types, there are only 7 reviews. These rare types of buyers may only find a few reviews from relevant customers. And therefore, due to uncertainty, they may only be willing to buy the item at a fairly low price. So now the customer's purchase decision, whether or not they're going to buy the item, is now it's not just a function of the price, but it depends on how certain the customer is about their values for the items for sale. And in turn, their certainty depends on the earlier sales and the reviews generated from those sales. And so this leads to a tension between, first of all, setting revenue optimal prices, high prices, but also ensuring that all of the buyers have enough reviews that they can confidently estimate their values for the items for sale. So to give an overview of the results, in this work, we introduce a model that simultaneously captures, first, the seller's pricing problem when they're trying to decide how should I set the price of the items for sale, the buyer's learning problem, because the buyers are learning from reviews about their values. And then finally, the motives through which the buyers are learning, which are the reviews. And so overall, we study how the seller can set these high revenue prices, so how they can optimize their prices according to the revenue. We provide a no-regret learning algorithm for this problem, as well as matching regret lower bounds. So with that overview, I'm not going to give a very brief mechanism design background because I know this is an area that might be new to many of you. So I'm going to talk about a very simple mechanism design setup where there's just a single item and a single buyer. So historically, we've assumed in economics that there's some distribution D over buyers' values for the item that governs how much they value the items for sale. So for example, this assumption, classical in economics, says that there's some distribution in my head that defines how much I value, say, a coffee. And when I walk by a coffee shop, I draw a number from this distribution. If my value is above the price, then I'll buy the coffee and I won't otherwise. And importantly, classical economics has assumed that this distribution over buyers' values is known a priori to the seller. And then the interaction between the buyer and seller kind of follows like this. The seller first uses their knowledge of this distribution over my values to select a price, P. And then the buyer draws a value, their value, from this distribution over values. And they decide to purchase the item if their value is at least the price. And so from this, you can see that the revenue maximizing price is going to be the one that maximizes the price times the probability that the buyer's value is at least that price. But the really kind of key assumption here, which may seem a little bit unrealistic, is that this assumes that the seller knows this distribution D, and moreover, that the buyer knows their own value before they even purchase the item. And in this work, we relax both of these assumptions, that the seller knows D and that the buyer even knows their own value before they purchase the item. Because after all, I certainly don't know this distribution governing how much I value coffee. Why would the seller know this distribution? I might think that I'll like the coffee, but I buy it and it's burnt. And turns out I didn't know my value before I bought the coffee. Okay, so now with this background, I'll move on to our particular model. So in this model, an item is going to be sold repeatedly to a sequence of buyers over the course of T rounds. And we're going to assume that these buyers are distinct. There are no repeat buyers. Each buyer is going to have a type. I'll call it I. They're D types. And so these could be, for example, the buyer's height, their weight, their skin type, etc. So maybe if we're looking at skincare products, the different types might be like normal skin, sensitive skin, oily skin, dry skin, etc. We're going to also assume that there's some unknown distribution P over types. So how common are these different types in the particular market, online store that we're looking at? Okay, so now, yes.
Sorry, the number of buyers that you're considering are multiple buyers per type, right? I mean,
at each time step, there's just a single buyer.
Okay, yes.
But there's capital T time steps.
Are there finitely many types?
Finitely many types, D types. Okay, so buyers of type I, their value for the item is going to be drawn from some distribution DI. And we're going to say the support of DI is between 0 and 1. And we're going to call its mean theta I. Okay, so a little bit of mechanism design terminology. We're going to refer to theta I as the buyer's ex ante value for the item for sale. And intuitively, you can think of this as what would the buyer expect their value to be before they actually purchase the item. This is the expectation of their value distribution. Now, let's sample V from DI. So this is what we refer to as their ex post value. And their ex post value is what their value actually is after they purchase the item. So I expected to like the coffee, but when I bought it, it was burnt, so I didn't actually like it. My ex post value was lower than my ex ante value. Okay, and what are we going to assume the seller knows? We're going to assume that the seller knows these ex ante values, the expectation of these distribution theta I from market research or whatnot, but not the distribution, any of the distributions themselves. For example, the distribution of our types or any of the buyer's value distributions. Okay, so now what does the actual online learning model look like? So at each time step t, ranging from 1 through capital T, there are going to be some reviews, sigma t minus 1, that describe past buyers' values, past buyers' types, and their ex post values. How much did they actually like the item after they purchased it? So maybe we've got these different types, like red circle type, orange square type, green triangle type, etc. And the reviews, the sigma t minus 1, tells us the past buyer's type together with their ex post value. How much did they actually like the item after they purchased it? So these are our reviews. Next, the seller is going to set some price PT between 0 and 1. The buyer is going to arrive. They have some type IT drawn from our type distribution. That buyer, they're going to observe the past reviews of past agents with that to share their type. So if this buyer's type is like oily skin, they're going to go back and look at the reviews of people who had oily skin. And they're going to, from these reviews, they're going to decide whether to purchase the item. I'm going to talk more about their purchase model in a minute, but they'll look at the reviews, decide whether or not to purchase the item. And one crucial thing to note here is that the seller doesn't know the type IT when they choose the price PT. In other words, they're not able to kind of discriminate on the type of the buyer when they choose the price. You can't set a different price for the different types. So if the buyer purchases the item, they pay the price, and they leave a review if they buy. So their review will be both their type and their ex post value. Ex post value is drawn from their value distribution. Mm-hmm.
How do they get the reviews?
So the reviews, we're just saying the reviews include their type, like oily skinned or whatnot. So more and more actually online stores are like including these fields where you input a little bit about yourself. So it could be like your height, it could be your skin type, things like that. So we assume that the reviews, or maybe it's just textual. Like in the Amazon example, I'd search for long-haired, and then you can see all the reviews by people who mention long-haired. So in any case, we assume the reviews mention the type and also that ex post value. Uh-huh.
Yeah, because like, does the model tolerate risk, like uncertainty over the type or no? Because
no, no. We are assuming the type is clearly communicated, but that's a good question. Okay, so a little bit more about the buyer's purchasing model. How do they decide whether or not to purchase the item based on the reviews? So we're going to say that the buyer's purchase decision is defined by some threshold. I'm going to call it tau t at time t. And this threshold depends on the past reviews and the buyer's type at that round. And so you can think of this tau t as the buyer's estimate of what their value likely is, what their ex ante value likely is based on the reviews. And the agent is going to purchase the item if the price is lower than this threshold that they're setting. So there's basically intuitively they're saying, I'll purchase if the price is lower than what I expect my value to be based on the reviews. Now, the choice of tau t, it can't be anything, and for the following reason. A conservative agent, you might have a very conservative agent who would choose this tau t to be very low. They don't want to take any risk. And in an extreme example, they just set tau t to be 0, and this would mean that they'd only buy the item if it was actually offered for free. And clearly optimizing revenue with an extremely conservative agent is basically just impossible. So we're going to set some limit on just how low tau t can be. So in particular, we're going to say tau t, it can be anything, but it has to be at least some lower confidence bound, I'm going to call it LBT, that equals the average of the reviews left by buyers who had the same type as the current type, minus some uncertainty term that depends on the number of those reviews. So basically like a turn-off bound type of, and I'll say this a little more firmly here. So we're going to say our agent is eta pessimistic if, let's say that this phi t are the reviews left by previous agents with type IT. So the agent's current type, look at the previous agents who had the same type. We're going to define LBT to be basically the average of those reviews of the agents with the same type, minus this standard kind of Chernoff confidence interval, which depends on the number of those reviews. And so we're going to finally say an agent is eta pessimistic if their threshold, which defines whether or not they purchase the item, is at least this lower bound. So this is the restriction we're putting on the agent's purchasing model so that revenue maximization is even possible. And okay, so this means that no matter what tau t is, as long as it satisfies this restriction, the agent will definitely buy if the price is below their lower bound. Okay, and just to give a little bit more context about this, it can be shown that with probability at least 1 minus eta, over all time steps, the agent's actual ex ante value is at least this lower bound, which makes sense because this does look just like a standard confidence interval. And so if the price is smaller than that lower bound, the agent's expected utility, which is their expected value minus the price, is most likely positive. And okay, so in other words, if we want to talk about this restriction intuitively, we're saying that a buyer will definitely buy if they have good reason to believe, based on the reviews, that their expected utility, value minus price, is at least 0. They're not walking away paying more than what they actually value the item. Okay, so now with all of this notation and model, let me restate kind of what the key challenge we face in this paper is. And it's, okay, first of all, like I mentioned, the seller does not know the agent's type when they're setting the price. And therefore, they don't know the number of reviews that the buyer is going to be using to make their value estimates. So if this IT is a very rare type, then that agent's lower confidence bound is going to be very low. So like in this picture, you can see, let's look at this square orange type. Let's say they're very rare, so that their confidence intervals are actually quite large. And in order for the seller to sell to this type of agent, they'd have to set a quite low price. So yeah, they'd have to set a very low price to ensure a purchase and a review from this orange type of agent. If this rare type's value is actually high, then it might be worthwhile to offer these low prices early on in order to kind of win over these rare but high value customers. But the seller has to make these decisions about who to win over without knowing the type at each round and without even knowing the distribution over types. So that's kind of the key challenge that we face in designing this pricing problem.
So what do you mean by value customer?
Yeah, I mean customers, let's see. This is if I could illustrate this better if this was a bit more, this is a larger picture, but you could imagine a larger picture where this theta was kind of shifted up. So they're a rare customer, but they have a very high value. So customers who are willing to buy Ferraris or something like that. Rare people, but if you get them, you can get a really high value out of them. Mm-hmm.
Just on the previous slide, I'm a bit confused by the tau notate, the difference between tau and lower bound.
Mm-hmm.
If the lower bound is the average of the previous reviews that people have left with what they've bought it for minus something, does this not just perpetually decrease as the time goes on?
Oh no, because if you're actually gathering reviews, this is going the thing down here. This is the number of reviews. So it's if everything goes right, this should be increasing. This lower bound should be increasing up to their actual ex ante value, the theta, which is the average. Does that make sense? So this term is decreasing as the number of reviews grows.
Yeah, but it's if the people only purchase an object if it is below their ex ante value, and then they leave the review of the value they bought it at. I would have thought this pushes down the values left inside of the reviews. Okay, yeah. Something we have to be really careful about is trying to understand how biased
this term becomes. So yeah, that's, I guess, part of the algorithm is trying to get unbiased kind of samples of this type from the buyers we actually are targeting and care about. Yeah.
So just one question. So
Yeah.
the seller doesn't know the buyer type, but
Yeah.
at the same time, based on the number of reviews that have been there so far, kind of knows the frequency of the type of buyers, right? Correct?
Yeah. So part of the algorithm is part of it is like there's two kind of things we have to do. Is one, estimate the frequency of the different buyer types, and two, kind of use that to optimize the price. So with that, let me get to the main results. I'll first describe the main results, and then I'll describe the algorithm. So we're going to be measuring the quality of our algorithm using this classic notion of regret. Let me explain what regret means in our setting. So here, regret is going to be the difference between, first, the algorithm's total expected revenue over all t rounds, and two, this is our baseline, the expected revenue of the optimal fixed price if the agents buy whenever their X ante value is above the price. So let me interpret these a little bit. First, under 2, so under our baseline, both the buyer and the seller know more than they do under the learning problem, which corresponds to 1. First of all, the seller knows all the distributions, type distribution, value distributions, etc. And so this means that he knows which customers he should be targeting in order to maximize revenue. Second, the buyers know their X ante values, theta 1 through theta d. And this means that the seller can extract more revenue than he could from uncertain buyers who will only buy if the price is low enough. So overall, our baseline that we're competing with has a lot more information about the buyers than the algorithm it does itself. So just to write this mathematically, let's say that BT is 1 if the buyer buys at round T at the price PT, and BT is 0 otherwise. Then we can write 1, the algorithm's total expected value. I guess there should be an expectation here, but it would be sum over all rounds, BT times the price you set. And now let's think about 2. So let's say that P star is the optimal price if the buyers always bought when their X ante value was above the price. So in other words, we got the price here, and we're saying, what's the probability that an randomly chosen agent's X ante value is above the price? So they always buy if their value is large enough. Then we can write 2 as, okay, sum over all time of the revenue of that price in expectation. So that's that price itself times the probability an agent buys. And so in other words, we can write the expected regret as the difference between our baseline's revenue and the revenue that we actually got. And again, I think there should be an expectation here. So that's regret. Now let me tell you about our main result. So our result.
Question?
Yeah.
Do you assume that the buyer's error is only sort of lower, is only in one direction, that it's always lower than the actual X ante, or could they also be estimating higher than their?
I guess that's actually just better for us. If they want to be optimistic and their price estimate is a little higher, that's only better for us. So we don't make any assumptions on that extent. Just what's bad for us is if they're super pessimistic and they only buy if the price is really low. And in that sense, we kind of need to constrain them to get.
Couldn't that change the optimal action? Against which we're comparing the no regret?
Yeah, so we're not, in our baseline, we're not assuming that the buyers are actually doing any learning anymore. We're just saying they know their X ante value and they'll buy if the price is above the X ante value. Okay, so to describe our results, let's say that Q-min is going to depend on this quantity Q-min, which is the minimum probability of any type. So we're taking the min over all types of their probability of appearing. Okay, and here's our theorem. We provide an algorithm such that if Q-min, the minimum appearance probability is not super tiny. So in other words, Qmin is at least d to the negative 2/3, d is the number of types, times t to the negative 1/3, t is the number of time steps. Then our regret is going to be square root of d divided by Qmin plus this term, lower order term of t to the 1/3, d to the 2/3. Meanwhile, if Qmin is tiny, very tiny, then our expected regret is going to be dominated by this term, t to the 2/3, d to the 1/3. And as I'll describe, we also provide lower bounds that match these two upper bounds up to lower order terms. And maybe just to put these regret bounds in a bit of context, if the seller only observed purchase decisions and not reviews, and the buyers are also not learning, then Kleinberg et al. Gave a t to the 2/3 regret bound. This can be improved to t to the 1/2 under distributional assumptions. And if the seller observes purchase decisions and reviews, then you can get a t to the 1/2 regret. But all of these assume that the buyer actually knows their own value. There's no learning going on for the buyer. So that's also one of the challenges that we're up against, that the buyers themselves are learning from past reviews. So now let me give you an idea of the algorithm. So, okay, I'm going to start with an overview. There's like two phases of our algorithm, but I'm going to start with an overview. So at a high level, our algorithm is going to maintain at each step t a set st of buyer types which it estimates. First of all, these buyer types have a sufficiently high value. It's worth targeting them. And they're not exceedingly rare. I don't have to set super low prices just to win them over. So intuitively, ST is a set of buyers that the algorithm is targeting. So maybe like over time, it decides it's going to target people with like dry skin, mature skin, dehydrated skin, for example. Okay, now how does it do this? So our algorithm is going to have two phases. In the first phase, the algorithm is going to offer the item for free. And in doing so, it's just going to get IID samples from the type distribution. So exactly, it can estimate how frequent the different types are. And it's going to set the set ST of types that it's targeting to be the set of types that appeared often enough. I won't kind of get into all the mathematical details about what often enough means, but yeah. Okay, so we've offered the item for free. We've gotten our IID samples. We have a sense of which types are frequent, which are rare. And now in the second phase, the algorithm is always going to set the price to be low enough that buyers in this set ST, the set it's targeting, always buy the item. And it's going to gradually eliminate types that it's targeting that it decides contribute too little revenue. So this is the overview, and maybe I'll go into these two steps in a tiny bit more detail. So the first phase. Like I said, the algorithm offers the item for free for some number of rounds, in particular t to the 1/3, d to the 2/3 rounds. So this is our phase, and maybe like we're using the same figures as before. We've got this red circle type, orange square type, green triangle type, and all of the red circle and the green triangle are pretty frequent, but we don't really see many orange squares. So that's a pretty rare type. And we're going to set Q to be the set of buyer types that appeared sufficiently often. So in this case, it would be red circle, green square, green triangle. That's the first phase. Now I'll give an overview of the second phase once more. So the algorithm is now, going forward, it's just going to completely ignore the types that are not in Q. And Q is those relatively frequent types. Completely ignore them. These customers are rare, and they're going to have more uncertainty about their type. So here's this orange guy that we're ignoring. They're going to have these really large confidence intervals. You'd have to set a really low price to actually get this buyer to buy. So it's just not worth it to target this type of customer. So in the second phase, we're only going to aim to optimize revenue with respect to the set of relatively frequent types Q. So to do so, I'm going to just define a little bit of notation. I'm going to say rev PQ is going to be the revenue of the price P. So it's going to be P times the probability that an agent's ex ante value is above the price, and that agent's value is in Q. So this is basically the expected revenue restricted to agents in Q. And we're going to say P star of Q is going to be the optimal price when we're just optimizing revenue with respect to these relatively frequent types in Q. And I'm just going to use this observation that this P star of Q is actually going to equal the ex ante value of some agent who is actually in Q. So it's going to be the ex ante value of some agent who appears relatively frequently. That's just kind of how the math works out. Now, okay, in the second phase, the algorithm is going to maintain the set ST of types that it's targeting, active types, so that with high probability, this special type, IQ, remains in ST, IQ corresponding to that optimal price. We're going to initially set ST to be the set of relatively frequent types, Q. And we're going to set the price low enough to ensure that for every active type, the buyer will buy. So you can see that in this picture here. These are two active types, right? Our set ST are initially set to be Q, so ignoring this orange guy who appears too frequently. We're just targeting red circle, green triangle, and so we're going to set the price to be right at the bottom of these guys' lower confidence bounds to ensure that they definitely will buy the item. They might buy the item at a higher price, but we're setting the price to be at their lower confidence bounds to ensure they definitely will buy the item. And moreover, this ensures a review if the buyer is in this active type.
How do you know that price? Because the price was free. It was completely free before.
Yeah, so it's based on this assumption, this lower confidence bound assumption, saying that if we set this price low enough, the buyer will definitely buy. It's possible they'd buy at a higher price.
But you have no indication whatsoever after the first phase, right?
No.
Because the item was free.
Yeah.
But the lower bound doesn't depend on the price,
It depends on the value.
on the value.
It depends on what? How do you get that lower bound? You just assume that it exists?
No, so we are saying that, okay, we define this lower bound to be for, say, this green triangle type, to be the average of the reviews, past reviews.
Oh, so it's in the past.
Yeah, of the past, yeah. So it's going to be the average of those reviews minus a confidence term.
So you
from the
assume
past.
that you...
We assume that, yeah, to make it this...
That you have an item before. That the same item was sold before and you have information on it.
Yeah, we're only ever selling a single item. It's got many copies of the same item over time.
But then why do you use the first phase? Because
I think confusion.
No.
The price is zero, but the value is how much the buyer would have been willing to pay.
But you don't know that.
No, that's exactly what the reviews give you.
Oh, the review is telling you how much they were willing to pay?
Yeah. Or it tells you their value for the item.
Okay. But that's,
Yeah,
it's a strong assumption.
Yeah, I mean, you could also restrict it somehow to 1 star, 2 star, 3 star, 4 star, 5 star, and there would be some loss there. But here we're assuming they just tell you their value. But I think it could definitely be extended to coarser review systems. Yeah. Okay, so now just the type elimination phase. This is the last thing I'll say about the second phase of this algorithm. Now for each active type I in the set ST, the algorithm is going to be estimating what it could have gotten from setting a price of theta I for this set Q. So it's maintaining these estimates of how good is this price with respect to the set Q. And remember, we're defining this notation rev theta IQ to be the price itself times the probability that an agent would have bought at that price, and that agent is an element of Q, the set of relatively frequent types. And doing this estimation, I just want to mention, actually takes some care, because at each round, we don't actually observe kind of the thing we would need to just use a Hufting bound. Like we could use a simple Hufting bound if we observed whether the agent on that round actually like would have bought at a price of theta I, and that agent's inside of Q, but we don't actually observe this. We're only able to observe these things. We only see the type of the agent if they bought. So actually creating these estimates of the revenue takes some care. And finally, the algorithm removes types from this set of active types if they estimate that the revenue that type is contributing is too small. So for example, if this is their estimate of the revenue from the first type, this is their estimate of the revenue from the second type, when this guy, the confidence intervals here fall below the lowest confidence interval here, we're just going to eliminate that first type from our active types, like a standard successive elimination algorithm.
So capital Q changes over time.
Yeah. So I'm calling it ST here, but yeah, ST is kind of instantiated at Q.
Oh, yeah, sure.
And then it evolves
ST
over time.
Coincides with capital Q at the beginning and then changes.
Yeah. Okay, so let me just summarize the algorithm one more time. So first we offer it for free to get these samples from the type distribution. And we set Q to be the set of types that appeared sufficiently often. Now in phase 2, we're only going to try to compete. We're going to ignore all the types that are not in Q, all the types that appear just too rarely. And we're just going to try to compete with the optimal price, P star of Q, which happens to equal some theta IQ, which is optimal with respect to the agents in Q. So to do this, we're going to maintain a set ST such that with high probability, this special type IQ is in that set ST over all rounds. And we're going to set the price low enough so that buyers in this set ST always buy. And finally, we're going to be estimating revenue for all the different types in ST, and we're going to be eliminating types from this active set who just contribute too little revenue. So that's the algorithm. Let's see. I probably have like 10 more minutes, 9 more minutes.
Yeah, more than that.
Oh, okay.
30 minutes.
Okay, I think I'll actually just skip this slide. But let me talk a little bit about what the proof looks like, our regret bound proof sketch. So remember, our regret bound depends on this minimum probability of any particular type. So, and our theorem is that if this minimum probability of any type is tiny, so Q min is much smaller than this d to the negative 2/3, t to the negative 1/3, then our expected revenue is dominated by t to the 2/3, d to the 1/3. And otherwise, we get this nice square root t dependence, t divided by Q min. And I'll just give an idea of like where these terms are coming from briefly in a couple of slides in this proof sketch. So let's go back to phase 1. Phase 1 is when we're offering the item for free. And this phase lasts t to the 1/3, d to the 2/3 rounds. And so this you can see, obviously we're gathering regret during this phase by offering the item for free. So you can see this term illustrated right here. Now in the second phase, the algorithm completely ignores these really rare types, and they only try to compete with the optimal price with respect to those frequent types, agents in Q. And competing with P star of Q instead of the actual optimal price adds some d to the 2/3, t to the 2/3, d to the 1/3 regret as well. Now, there's this also factor in the second phase that the algorithm is maintaining these estimates of the revenues of the different active types for every active type. And obviously, these estimates are going to have some error. And the error of these estimates contributes about square root t to our overall regret, which is dominated by the terms I have on the top. And the final element of where are these regret problems coming from is that the agents themselves are learning. And this increases the regret by about d to the 1/3, d to the 1/3, t to the 1/3, which is again dominated by these other terms. So overall, that's where these regret bounds are coming from. And I'll just mention what happens if what happens when cumin isn't tiny? So that sketch was what for cumin was tiny. What about when cumin isn't tiny and we get this nice square root t dependence on the regret? Well, basically, we have the same analysis structure, but we prove that with high probability, Q, the set of fairly active or fairly frequent types, is actually the entire set D. And that makes sense because the whole point in here is that Q min is not tiny in this part of the analysis. So Q is the entire set D. And this means that we don't have to worry about like optimizing revenue but ignoring some types or anything like that. We can just optimize revenue with respect to the entire set of all types. And this significantly reduces the different sources of regret. So now let me...
So this first part, in the previous case, is enough both to cover the regret from the initial set of types that you're losing in phase 1 as well as the maybe additional types you're losing in phase 2?
Sorry, can you repeat the question?
So in the first case, when cumin is tiny.
Yeah.
So the additional regret. So it seems so that bound covers also all types you're losing throughout the algorithm, both in the first phase and in the second phase, because you may be losing additional types in the second phase.
Yeah, I guess the regret from the first phase, it is what it is. It's always t to the 1/3, d to the 2/3 rounds, no matter if Q min is large. We don't need to know Q min for the algorithm. So yeah, the differentiation when Q min is tiny versus large comes from the second phase. And basically it's just because we're just totally forgetting about the agents who are not in Q, not who are very rare. But it turns out, like, when Q min is not tiny, that set is just the set of all types. Everyone is pretty common, frequent. So we don't lose revenue by kind of doing this step where we just ignore the agents. Does that make sense? Okay, great.
How much is your proof dependent on the zero price? I mean, you probably know how much it costs to actually get the item, produce the item, right? So if you put the price at that level, does that change the proof?
Yeah. So I think I understand what you're asking. So this is, as I framed this problem, it's really about revenue maximization as opposed to profit. So I guess you could think of it as we're saying this is a zero cost item or something like that. I think it would probably like immediately extend to there being some cost to produce the item and you're unwilling to set, It's possible actually though, that could be interesting because I think we would kind of need to sell the item for free at the very beginning. So you might incur regret from, producing the item, but selling it for free at the beginning. So that would be another source of regret you need to be careful about. I think you would still get about the same bounds though, because fortunately that first phase is just relatively short in the grand scheme of things. Yeah, that's an interesting question.
Not directly related to this, but often when companies introduce a new product, their first goal is what's it called? Getting a market share rather than making a profit. So insertion into the market. So they're often willing to sell at a loss.
Yeah. The question I had is that if you buy it. And if this is an item that you buy multiple times, you may be upset because the price is increasing.
I agree. It's not related to that.
So I think that's outside the scope of the talk, but it's an interesting effect that you can get some of the buyers saying, "Oh wow, they are really raising the price at this point, and my valuation is."
Yeah, that's true.
My valuation. Right?
Yeah, there's all types of behavioral.
But in that context, offering it to zero price, I think is good, right? I mean, because there will not be the buyer will not perceive it as an increase of price. It's just saying that is given from.
And I agree with that. I mean, that's a good point. That's a very good point.
Yeah.
Also, there's the assumption there's no repeat buyers, right?
I agree.
Yeah, definitely going from free to not free, that seems like something I can live with. But if I came back later and it had continued to increase, then it could be upsetting. So a little bit about the lower bound. So we prove this Q min, so Q min being the lowest probability any type shows up, Q-min independent lower bound of t to the 2/3 d to the 1/3. But when Q-min is not tiny, Q-min is at least t to the 1/3 d to the negative 2/3. We have this lower bound of t over Q-min, square root of t over Q-min, showing that this 1 over Q-min term is kind of unavoidable. So I'll just say a little bit just about the intuition. So in our worst case construction to prove these lower bounds, we're going to have different types who have a similar value distribution, but large variation in how frequently they actually appear. And so intuitively, any algorithm needs to decide, will I target the low probability buyers who certainly will have these low confidence intervals? Or will I ignore those low probability buyers and just try to target the relatively frequent buyers? And either way, in either of these two extremes, the algorithm is going to suffer some high regret. And we show that actually no algorithm really can do better than these two extremes of either just target the low probability customers or all buyers, in other words, or ignore the low probability buyers. So yeah, that's the intuition. There are these two extremes. No algorithm can do better than these two extremes, and these two extremes incur the regret from the previous slide. And just a little bit about like some insights we can get from this lower bound proof. This, like I said, the proof indicates that any policy can't really do better than kind of choosing ahead of time, a priori at the beginning of time, to target all customer types, or just only focus on those high probability types that appear fairly frequently. In other words, this kind of the insights we can get from this proof is that it doesn't help to dynamically change over time which types of customers you're targeting. And interestingly, this mirrors the behavior of our actual algorithm that gets the regret upper bounds as well. Because we have this short initial phase to eliminate those low probability types, and thereon we're just going to target the fairly high probability types. So yeah, this is just an interesting insight that kind of connects our lower bound proof to our actual algorithm. So now I'm just going to wrap up, I think a little early, with some conclusions and future directions. So conclusions, just a summary. So we give these no regret pricing strategies when both sides of the market, both the seller and the buyers, are learning from reviews. Our algorithm strategically sets these lower prices earlier on, and this allows us to boost sales from customers who have somewhat rare types but high values. And in doing so, our algorithm has to carefully trade off the revenue loss that we occur from giving discounts in the initial phase with the potential for future revenue gains. We also have this lower bound showing that our algorithm is optimal up to lower order terms. So a few future directions. You know, in the real world, people don't always leave reviews when they buy the item. And so one direction would be to give these pricing strategies when buyers don't always leave reviews when they buy the item. And this would mirror these real-world buyer behaviors because research has shown that probabilities of reviews generally have this J-shaped curve, where you can look at the buyer's value for the item along the x-axis and look at their probability of leaving a review along the y-axis. And typically reviews on Amazon or whatnot follow this J-shaped curve, where if an agent really doesn't like the item or they really like the item, they're probably going to leave a review. But if they just kind of feel neutral about the item, they're probably not going to leave a review. So I think this is a really interesting dynamic that hasn't been studied in this kind of pricing literature.
So you can use that for estimating the values.
Yeah. It could. Yeah, it's unfortunate. In some sense, it's unfortunate because if you were to just get IID samples from like the value distribution plus this randomness, they'd be really biased. But there is information kind of about the value encoded in that bias. And last, kind of related to this discussion we were having, what if the buyers actually appear over several rounds? You have repeat buyers. And one of the real challenges here would be that buyers may actually behave strategically early on in their interactions with the seller in order to purchase at lower future prices. So if a buyer knows that the seller is doing this kind of pricing via learning, the buyer may behave strategically early on in order to get lower prices later on with knowledge of this machine learning algorithm that the seller is using. So that introduced like a host of complications. But it's related to prior research where buyers behave strategically over many interactions in order to get this good long-term utility. And the key difference between us and that prior research is that here the buyers actually know their value. We have this added complication that the buyers just don't even know their values.
But here also there's another aspect. I don't know, maybe you refer to that, but strategic behavior could also be strategically relying about the review.
Yeah, that too.
It doesn't just need to be buying or not buying the item if the value is high. That's true. I might say I hated this item so that they'll set lower prices in the future. And or that I'm a different type.
Yeah. There's many strategic elements that could come into play here. With that, I'll wrap up. Thank you very much.